coming with that a bit discussion with that the L1 and L2 caches, basically that the development that okay, when that the cache memory has been developed into the computer system, on that time it has found that okay, for because of the cache memory, the CPU's performance have been increased dramatically. So that is what from there actually the concepts comes that okay, how about to make that the level of caches. So that means if there are several level of caches, it may be much more effective. And actually, it has found that yes, it is correct. So we are going to be discussed here. So that the L1 cache first is saved memory access cycle time is greater than the processing unit for an instruction execution. Right. So this is what actually already we have known that we are trying to accessing from the CPU to that the memory something that it is going to be take time during a program execution into that the processor. So if that something is missing, then the CPU must need to be request to that the main memory RAM. So if it is the RAM must need to be searched that instruction and then send it to back. So by that the time it is requesting and it is responding by the RAM to that the CPU. By that the time CPU is not doing anything. So that's from that the cache memory concept comes. So that is the problem that the main memory is not that much faster that our CPU is. So that the problems comes, and that's why yes, the L1 cache has been developed, and its saved memory access cycle time is greater than the processing unit for an instruction execution. Therefore, instruction cache memory inside the processor is used for issuing the instructions to the execution unit at a faster rate. So that is what it has not only developed that the L1 cache, but also it has been said that okay, if it is a smaller size of cache, then it is going to be more quickly it's possible by the processor to get that the operand it's looking for. The level on cache is typically with this type of kilobytes, 8 to 128 kilobytes, which is operates at the same clock frequency as the rest of the CPU. So these are the talking about the size, and it's telling that the same clock frequency is going to be needed. And however, for caches, data and instructions are often stored in separate data and instruction caches. So that means it is telling that okay, it can happen that the L1 cache are having that the two units, that is the instruction cache and the data cache. So this is actually if that in a processor the L1 cache is actually into this with the two parts for the instruction and for the data. If there are two units are there, simply we call it actually that the unified cache. So you should have to remember that the L1 cache is are having that the two part. One is for the instruction, one is for the data. So instruction cache, data cache. So if the both of them are there in the L1 level cache, then it is known as the unified cache. So that is the concept here. So this is actually trying to show that from memory that the L1 cache is going to be stored the instructions as well as the data. So based on that the inputs you are giving, and then the processor is going to be fetch the instructions, fetch the data, and take that the appropriate actions. If you're looking to that the L2 cache, then the level 2 cache is normally much bigger. Like actually that can be the double the size of the L1 cache. So you can see that the size of like 128 from the 256, and then again plus it is multiply the 256. So multiply that to again 2. So you can see that it is increasing double every time. So maybe this is now this L2 caches with the maybe the 2 or 3 megabytes these days. Okay, so in the recent processors. So in the earlier processor generations, the L2 cache was placed outside of the chip, either on the motherboard, as in the original Pentium processor, or in a separate special module together with the CPU. So this is quite interesting. That maybe this can be surprised you that how it can be a processor, but yes, it is that the processor for the Pentium 2. So actually they have tried. It was a module like the CPU's. There was a CPU slot during that time, so they are not using the socket on that time. Actually, they tried to that the CPU slot, CPU stick like that. This is look like the memory stick that we have seen before. So this is actually that circuit board on that you can see here that we are having the CPU, and actually this CPU is actually slotted into that the memory slot. So sorry, not memory slot, CPU slot. Okay, so on that you can see that there are two chips. These two chips are actually the L2 caches chips onto that this circuit board. So you can see that here it has written that together with L2 cache, which is two chips here, right? The whole module is installed in a socket on the motherboard, but this design is no longer used. So this is that the fact here that we are not using that the processor into that this type of modules anymore. Rather than we are actually using as a processor as a square shape like that, and we are installing it into the CPU socket. So now that the cache memory is basically inside of the processor. So this is what the L1 L2 caches is giving us information that okay, how that the different processors are placing that the L1 and L2 caches. So this table is giving some idea for that some older processor like when that the Pentium K5, K6 that are the external, L2 cache is external. So in the case of that this processor's time, the L2 cache is actually placed on that the motherboard. Okay. So Pentium Pro that is internal in the CPU. So inside of that both of L1 and L2 cache was there. In that case L1 cache was inside of the processor and L2 cache on the motherboard. In the Pentium 2 external. So that means in the Pentium 2 and Athlon, this processor's L1 cache was inside of the processor and L2 cache was outside of the processor on the board actually. The Celeron first generation they did not consider any L2 caches, and Celeron later versions and Pentium 3, Athlon XP. So that the Athlon is actually that your AMD processors. The Pentium 4, so these are the Intel ARM. So now actually these days we are having that L1, L2 and L3 caches, and all these three levels of cache are placed inside the processor. So we are here only talking about the L2 caches. So you can see in this figure that we are having this is my processor, and this is my processor core, that the yellow box, and then we are having the L1 instruction cache and data cache. So this is my level 1 cache, and then later on that the black box here you are saying that is the L2 cache. So that they are placed inside of the processor. Now these days all the three level of caches are inside the processor, and then this processor is actually connected with the RAM, so that the NOT bridge that we have learned from that the motherboard block diagram that chipset block diagram that we have studied. So you know that from the CPU how the RAM is going to be connected to that the RAM chipset, right? So this is how that it is showing that how that the L1 and L2 place into that the same processor inside of the same processor. So we are having the CPU core, and then you are having that the L1 and L1 instruction cache. So this is actually unified cache, L1 instruction cache and L1 data cache, and then L2 caches is placed. So it is talking about that not only improving that the L1 and L2 caches, but also you should have to look after that the bus lines you are using. We already said that the most traffic areas is between the CPU, RAM, and the AGP card, so that the traffic is going to be high. So you must have to be ensured that the bus lines are much more powerful in that areas. So it is here of talking about that L1 and L2 caches powerful buses. So it is telling the bus between the L1 and L2 cache is presumably the place in the processor architecture which has the greatest need for high bandwidth. So it is required that you are getting that high bandwidth bus lines between this L1 and L2 caches. So here again that giving some of the CPU's informations, and it has shown that actually how the development has been done for each of that processor with that the L1 and L2 caches. So you can see here the bus wide for the first three processors here, the 64-bit, but look that the clock frequencies are different. That the AMD Athlon XP Plus, AMD Athlon X64, so you can see that their bus clock frequency has been improved significantly. While the Pentium 3, the clock frequency is less, but theoretical bandwidth also, it is going to be, increased from the top to bottom. So you can see that Athlon XP 64FX, the next version, again the clock frequencies has been increased, same clock frequency is same, but they have increased that the bus wide, as well as therefore that the theoretical bandwidth also improved. In the case of Intel Pentium 4, that you can see that from 64 directly they come to the 256 bits, and they are having the more clock frequency than the AMD processors here we listed. So that means the bandwidth is going to be better. So that is what telling that actually if you are having that the better clock frequencies and bus wides, then actually you can having that the more bandwidth. So how that the bandwidth is calculated is simply that bus wide multiply that the clock frequency and divided by 8. So this is the formula used to calculate this bandwidth. and it's showing that, I mean, if you are having that the more clock frequency and bus widths, that means if the theoretical bandwidth is going to be higher. So now if you're looking to that the different systems here, that for the L1 and L caches, so AMDs have settled fairly. So this is one of the discussion here. It has been made that, I mean, how that the AMD and that the Intel, that the I mean, they have approached with the different level of caches. So their actually approach was different. So let's take that AMD have settled on a fairly large L1 cache. So they're keeping that the L1 cache with the 120 kilobyte, while the Intel continue to use relatively small but efficient L1 caches. So that means the Intel AMD was thinking that, okay, no, I can use that larger size L1 cache, but the Intel thinking no, that always keeping that the L1 cache smaller size is going to be better. So on the other hand, Intel uses a 256-bit wide bus on the inside edge of the L2 cache into that Pentium 4, while AMD only use the 64. So that is what the difference. So that, I mean, you can see that the Intel has kept the L1 cache smaller, but they have take that the more bus wide, the 256. But AMD is making that the L1 cache larger, but they are not keeping that the bus width actually that much bigger size. So that is the bus width is smaller. So that means this is the difference that the two companies has think. I mean, think that the two-way. Their think tank was thinking that the approach has been the two ways. So AMD uses explosive caches in all their CPUs. It means that the same data can be present in both caches at the same time, and that is clear advantage. It's not like that the Intel. So this is what an approach has been used, the explosive caches, and this is what, I mean, it is telling that in the same time that data cannot be present, okay, into that the both caches. So that common data is not going to be there into that the both caches. That is that they are telling, and that is possible for the exclusive caches. But in case of the Pentium 4, it has a more advanced cache design, that is the execution trace cache. So that the techniques they have used, making up 12 kilobyte of the 20 kilobyte level 1 cache. So this is the instruction cache towards for coded instruction. So that L1 is taking that the Pentium 4 has taken that the different approach, the execution trace cache, and with that they are actually making up the 12 kilobyte of that the 20 kilobyte level 1 cache. So this is what it is showing, that the different technologies, different thinking that those the processors level of cache, that they are thinking in a different way. So here you can see that some of the processors have been shown, that the Athlon XP using that L1 cache and L2 cache, 120 kilobyte, 256, 128, 512 for the Athlon. These are the AMD processors, and in case of the Intel processor, you can see that the L1 cache size is very small, the 20 kilobyte only, but that Athlon is actually using 128 kilobyte. So you can see that they are the L2 cache size is actually similar like that the AMD processors, but in case of that the Pentium is using the smaller size of L1 cache. Look that if you are looking to the further, then they have kept that the L1 cache, the AMD processors 128 kilobyte as well, but they have actually increased that the L2 cache size from the 256 to the 512, and from the 512 to the 1024 kilobyte. So now that the Pentium 4 is coming with that, they have made that the L1 cache shorter, 28 kilobyte, and they have in L1 cache they have make it double that what they had before in the last version. So this is what they are trying to show here. So this is what the all RAM storage has a certain latency, which means that a certain number of clock ticks must pass between, for example, 2 reads. L1 cache has less latency than that the L2 cache is more efficient. So this is what it is talking about, that about the latency. That look that if you're looking to this, that the processors of Pentium 4, Pentium 2, Pentium 4, and Athlon XP, then you will understand what the latency is. The latency is that, I mean, how long time actually it is going to be take to get the service. So how many cycles you need to actually get the service. So more cycles it is going to be need. That is means that more time you are going to be need to get the service from the computer system. So that the latency of L1 cache in case of Pentium 2, that you can see that the 3 cycles, Athlon XP the 3 cycles, but Pentium 4 having the 2 cycles. In case of the L2 cache, that the Pentium 2 18 cycles, Athlon XP only 6 cycles, and Pentium 4 is that the 5 cycles. So both cases, if you're comparing here, in both cases you can see that the Pentium 4 is needs that the least number of cycles for executing the instructions. So it's suggesting that the Pentium 4 is better than the Athlon XP here. And why? How it is possible? How it made possible? That made possible through that the you can see that the cache size and that the bus wide. So if you are looking to that the Pentium, that it is using the 256 bits bus wide, and the Pentium the Intel Pentium 4, and you are using here the Pentium 4 that is using the 28 kilobyte cache and L2 1024 level of cache. But if you're looking to that the Athlon XP, then you can see that the Athlon XP has been used that the 64-bit bus wide only, that the smaller size bus wide, and it has using Athlon XP. It is using 128 kilobyte bus wide level 1 cache and level 2 cache as well. So that means that the think tank that they are planning here, they have shown for the AMD and that the Intel processor, we can easily find it out that the Intel think tank was much better than the Athlon XP, as because Pentium 4 has significantly improved that the latency. The latency has been getting less with that the think tank of the Pentium, but not with the Athlon XP. So the Pentium 4 is much better in case of this comparison that actually we can see here on. Okay, do you understand?
Yes, sir.
Okay, so yeah, I have to move now. So just wait for a minute. I'm going to be connect from the mobile phone. So you have this file, right? The lecture 3, Ashik?
Yes, sir.
So please you share it on the slide, okay? Then I'll continue the discussions. Okay.
Okay, sir.
I'm leaving from here on. I'm joining from that my mobile phone. Thank you. Please wait for 2 minutes. I'm coming.
Sure, sir. जो तुम न हो रहेंगे हम नहीं. जो तुम न हो रहेंगे हम नहीं.
Yeah, Kamrujaman. Ashikujaman, sorry, Ashik.
Yes, sir. May I share?
Can you please share the screen? I mean, with
Sure,
that
sir.
lecture 3. I'm extremely sorry. I mean, please, I mean, accept my apology that
Okay, sir.
today actually I'm busy.
So, can you
So,
see?
yeah, now I can see this. Yeah, so here we are talking about the transistors, right? So, yeah, so I think that we have understood that actually that the L1 and L2 cache development that we have discussed that today. So I think that we have understood that, okay, how that, I mean, the L1 and L2 cache development has been done. So it was a very good, I mean, way that the way, I mean, the explanation you have got. I have, of course, collected it from the book and internet. So this information is telling us that actually how to do work with the topic to show that how the development is ongoing. So that the topic you have got for you doing your project, that you have to be make sure that you are also thinking this way, that you are going to be show that, I mean, the development for each of the component you have got for project work. So every decades you are selecting one of the component. It can be RAM, it can be the processor, it can be that motherboard, based on that the topic actually you have got for project. So you should have to also think this way, that okay, how the development is actually coming, how the development is happening. So yes, I think that, I mean, there is a less opportunity to do the work with that the different type of processors. Like that, I have said to select only one processor for each ticket, but it could be better that, I mean, if you could select the one processor for Intel from a ticket, one processor from that the AMD from a ticket. So that's from the same ticket. If you could actually explain select that the two brand processors, and this way if you study that, I mean, for that all the from the all the decades from that the birth of the processor to that that current moment, then you could see actually more clearly that how the development is actually have been done for that AMD processor and the Intel processor. But as because we are doing the things in online, So it might not be possible, and that's why the reason I have said, okay, select only one processor, so that actually you can at least see that, okay, what are the changes have been made into the processor. So yes, I mean, later on that, I mean, the L1 cache, L2 cache, and then it came the L3 cache. So there is a bit more discussion is needed that is actually not included in the slide or into your notes. That is, I mean, about the L3 cache. Is that, I mean, this was, I mean, habit that, okay, when it has found that L1 cache was, I mean, cache memory was effective, on that time they bring it as a L1 cache and L2 cache. And when they found that, okay, with that the L1 and L2 cache both are effective, then they have thought, why don't we actually increase the level of cache? So they have increased the cache level from L1, L2, and M3. Of course, that L1 is smallest one, and then L2 is that the bigger than L1, and L3 is much bigger than that L1 and L2. So, I mean, these are the three level of cache. It has been found that yes, I mean, it is very effective. And it, as I say, that it become habit. When you see that, okay, if I'm following these routines or if I'm following these guidelines, then I'm getting the improvement. So you're going to be making it as a habit. Okay, so the same way that L4 level 4 cache also implemented. So in that the level 4 cache, I mean, they have taken it out, the level 4 cache, and it has been found that the level 4 cache was also effective, but it is actually not mandatory. So simply, why we are doing this discussion is that simply it's not like that. I mean, if you're getting the improvement with something, and if you're trying to just increasing the levels of that improvements or techniques, it's not going to be simply make your system better. Okay, so you should have to be, I mean, there is a limit. So that is the L3. So it has been decided that, okay, we are going to be have that the L3 level 3 caches, up to that the level 3 caches we are going to be have into our CPU, and that is going to be much more enough. So that is what, I mean, this is that we are going to see with that the pipeline technology also when we are going to be discuss it. So that is the later time we are going to be discussed on. Okay, can you please go to that the next slide, Ashikujaman?
Transistor, sir.
Yeah, transistor. So yes, I mean, this is that the transistor we are talking about, that is actually known as a MOS transistor. So the MOS means here the metal oxide silicon. So this transistor is most common type of transistor used to design integrated circuits. So this is a common, I mean, it is that the, I mean, everywhere the use of MOS transistor will be able to see when we are going to be talk about that the computer architecture. So the MOS transistor have two negative charged areas. That one is going to be the source, that which has an almost zero charge, and another is going to be the drain, that is going to be with that the 5-volt charge. So they are separated by a positively charged region called the substrate. So if you're looking to that the figure below figure to the left side, so you can see that in the left side we are having the source that with the minus sign, that the white box left side, and then the right side you can see that there is another white box that is actually drain. So that is also the negatively charged silicon. So here that you can see that these two boxes, the white boxes, are separated with a substrate that is the positive charged silicon. So this is actually separated, this source and drain. So when you are applying, there is an on the top of, you can see in the between that there is a black thermal paste. So on the top of that you are having a electrode. So that is actually saying that the substrate has a control electrode overlaid called a gate that allows a charge to be applied to the substrate. So in the right figure, if you're looking that when you are applying the charge, the 5 plus 5 volt into the electrode, then what is going to be happen? Then it is going to be happen that the positive charges of the substrate are repelled, and a negatively charged communication channel is going to be open between the source and drain. So you can see that now that source and drain is connected with that the negative charge. So this communication channel has been built up between the source and drain. So this is actually showing in this slide what we have found. This is actually just showing that how the transistor works. Okay, that how a MOS transistor works. So when there is no charge into the electrode, the left side figure is showing that, okay, the substrate is going to be I mean make a barrier between that the source and drain,
and when that the voltage is going to be applied onto the electrode, on that time this is going to negatively charge communications, I mean between source and drain, is going to be developed. So that is actually, it is just trying to show to you that okay, how the MOS transistor works. Okay, go to the next. This is the concept we are going to be find it out. We need it when we are going to be discuss about the SRAM and DRAM. On that time we have to need it, this because that the RAM cell we are having, that is actually using that the MOS technology. So in case of SRAM as well as in case of, I say that, I mean it is actually a regular, I mean it's a common thing that actually we are using in every part of the computer system, that the MOS transistor. So it's required, and the reason behind it is actually that, I mean they can be easily used for designing the integrated circuit. So this is actually is a useful thing of that MOS transistor. Can you please go to the next slide, Ashik?
Yes, sir.
Yeah. So here it is talking about that that okay, yeah, that there are generation by generation the CPU is coming, and here it is showing that from Intel that what are the CPUs comes for the 7th generation, and the number of transistor in the Pentium 3 and 4 includes the L2 cache. So here it is trying to show just simply that with the table that okay, from that 8088 to that the Pentium 4 Prescott, that if you're looking from the right side column, then you will find it out that how many transistors are day by day just simply, I mean increasing in a single processor. I mean you are using the look at billions of transistors. So that is what it is trying to show, that okay, how that, I mean day by day, now the release year of the processor, 7th generation processors, and with the clock frequency and the number of transistors. So you can see that the number of transistors have been improved, I mean increasing significantly. You need it, you need it, because I mean day by day that your requirements, your demands are increasing, that okay, you want to make CPU to do more works. Okay, so to more that you are getting that the advanced components of the computer system day by day, like you are having that the better graphics card, GPU you are having in the graphics card, and then you are having that the I mean more faster CPUs, you are having that the bigger size of RAM with new technologies. So that means definitely that you are going to be need the more instructions, more transistors to control those more newer technology that is actually coming with the CPUs and other components as well. Okay, go to the next. Yeah. So this is the, I mean discussion of the pipeline technology. So this is what, remember that the things we are discussing here, because of the two things. One is that, I mean because of the fetching, right? So we have said the fetching, if you're doing from the CPU to the RAM, then it is going to be take much time. So if your CPU needs something during the operations, it must need to be go to the RAM. So we do not want this type of fetching every time. That while we do not want this type of fetching every time while that, while that the CPU is executing something. So that is actually the problem. That is actually said always this is coming when you are discussing about the computer system, the CPU, RAM, and graphics card. So when you are talking about the top part, top level part of the computer, then always it comes into the discussion that the memory is not faster. Memory is, RAM is slower than that your the processor. So the processor is the fastest component. So this is the getting the, I mean main problem, and that's why this, to reduce this problem, actually that the two techniques has been applied into that the CPU, that you can see that one of that we have discussed already, the cache memory, and the second one is that the pipeline. So what is that the pipeline technology is? So it is telling that the pipeline is technology that improves instruction execution speed by putting the steps into parallel. So the concept is here similar like that the cache memory. Concept is here that okay, I mean what is actually going to be, this is that the, I think that you can remember that the data and instructions that we have discussed. So we have discussed about the sys chips and RISC chips. So from that the discussions we have learned that okay, when you are getting a bigger size of instruction set, we just break it and we make that the sub-ops. So exactly that the pipeline is also doing that. So in that the processor, the instructions are sent from the software and broken down into the micro ops. in the CPU. This decomposition execution takes place in the pipeline. So that is what that a group of instruction comes. A set instruction comes that is going to be break down and make some some ops. Okay, so smaller it is going to be break down and make the smaller size of sub operations, so that the sub operations are going to be delivered, are going to be handled parallelly by the processor. So that means what is going to be happen, that the same concept that we said in the library, that if you are having a single libraryman, 40 students in a queue, so one by one will get the service, it is going to be take them time. So if there is the two librarymans, then the queue is going to be divided into two. If the three librarymans, queue is going to be divided by three. So this is what that the service time is going to be better. So this is what the same thing, the same concept is here, that it is trying to tell to you. In the pipeline, the first 6 instructions are decoded and converted into digested micro instructions. Then these are processed at a time in rest of the pipeline. The pipeline is made up of a number of stages. Older processor have only few stage, and the newer processor have the many. So this is the same concept, that when it has found that pipeline is effective, then they are trying to increase the stages of the pipeline. They are thinking that, okay, if you're having that the more pipelines, that is going to be very useful. But there is also a limit. We are going to be discussed in the upcoming slides. So at each stage, something is going to be done with the instruction, and each stage requires one clock tick from the processor. So yes, that is the fact, that if you are having the 3 steps for the parallelly, that if you need the 3 stage, so that means in the 3 stage that there are going to be some, like that the fetch, decode, execute we have seen. So that means every stage should need to be followed with at the same time. At the same time, they are going to be start, but with a technique that should need to be followed. There should not be any conflicts. That okay, first instruction, sub operation is doing the fetching. The second operation should not do the fetching. Second stage should not start with the fetching. Immediately. So at the same time, the fetching stage is not going to be considered for that the subgroups. If it is there, then the CPU is going to be confused how to execute the things. So anyway, so we are going to be discuss it into that the 5 stages. That the next slide. Go to the next slide. Yeah. So this is that the pipelines, that the execution phases of an instruction for a processor with a 5-step classic pipeline are as follows. So this is the classic 5 steps that can be actually applied for the sub operations that we said. After breaking down that the set of instructions, then the sub operations can be some ops can be actually taken into this 5 stages. So that the 5 stages, what are the 5 stages are that you can actually see here, that the fetch, decode, execute, and memory, and write back. So these are the 5 stages. The classical pipeline has been introduced. So can we stop the discussion here on?
Sure.
Maybe that tomorrow's class we are going to be start from here on. Okay.
All right, sir.
Okay, sir. Thank
Do
you.
you have any
Okay,
questions?
sir.
That what are the things we have discussed today? Do you have any questions? Whatever the things we have discussed today.
No, sir.
No, sir. Yes, sir.
Okay, so I'm extremely
No,
sorry
sir.
again. Accept my apology that I'm outside, so I know that there are too much noise today. Okay, so then okay, so tomorrow we are going to be finish this lecture, and we are going to be get the question.